So just a minute. All right, thanks everyone for joining us today for Virtual Lab Notes. We're excited to have you here and just want to make sure that everyone can see and hear me. And so if you're having any issues, please put that in the chat. But make sure as well that your microphone is muted and that you turn off your video using the buttons at the bottom. Make sure that they're both red, just so we can save bandwidth and we can all hear Dr. Burnley and her amazing lecture that she's prepared for us today. You can also use the chat function for any questions. Feel free to ask them as they come up during the presentation. I'll read them to Dr. Burnley at the end, and we'll go through and kind of talk through any of them, and she can answer anything that may come to your mind. So feel free to just pop it in the chat. If during the presentation you encounter any issues, there is a link right here, support.google.com/meet. That you can check out and have any questions there. I can do my best to troubleshoot as well if you want to just message me on the chat. And as you can tell, we are recording today's session and it will be available at this website following this lecture, probably next week. We try to get up within the week. Before we get going though, I just wanted to let you all know about next month's Virtual Lab Notes. It'll be on Wednesday, June 30th, and it will be with Dr. Corey Rusenick, who's an assistant professor in the Department of Chemistry and Biochemistry. We're still discussing a topic, so there's not a firm topic yet, but I will get you on the marketing emails and that so you can come and listen to Dr. Rusenick and learn more about his work and what he does in the Department of Chemistry and Biochemistry. And so with that, I would like to introduce Dr. Pamela Burnley. She's a professor in the Department of Geoscience here at UNLV. We love Dr. Burnley. She's great, works really closely with a lot of our students. And the title of her lecture today is How Do We Know That the Earth is Not Hollow? And just a few quick notes about Dr. Burnley before we begin. She earned her PhD in geology in 1990 at the University of California, Davis. She held postdoctoral research positions at Cornell University, Princeton University, and the University of Colorado at Boulder. She was an associate professor in geology at Georgia State University before coming to UNLV in 2007. She is a fellow of the Mineralogical Society of America and is currently serving as its vice president. Her research is funded through grants from the National Science Foundation, Department of Energy, and Department of Defense. And we're very excited to have Dr. Burnley here with us and her lecture on how do we know that the Earth is not hollow. And with that, I will turn it over to you, Dr. Burnley.
Okay. Hi, everybody. Thank you for being here. I am, like the rest of you, going to turn off my video so that we don't have any bandwidth issues. And then I'm going to go ahead and share my screen. So 2 seconds, bear with me. Okay. So, no. Okay. So Corey, can you let me know if I am in presentation mode or if I need to redo this?
You need to redo. It's not in presentation mode.
Yeah. Sorry about that, folks.
That's okay. The technicalities of Google Meet, I think, catch all of us. So
yeah, we had this figured out the first time.
It was select a window.
Yes. No, it's not. Okay, hold on. Wrong window. Let me see. Let me try another one. Here it is. There it is. There it is. Okay. Okay, so this should be better, right?
There it is.
Okay, great. So thank you all for coming today. I chose the title of my talk because I work on the deep earth. That is my field area. And it's maybe a bit of an abstract topic that most people don't think about. So I thought it would be kind of intriguing to ask the question, how do we know the earth is not hollow? Because that's an interesting alternative idea that we see in fiction and sometimes other places. But before we get started, I really need to acknowledge the people who help me with my research, because hopefully I'm going to spend a little bit of time talking about my own research as well as the research of many other people. My research is conducted with my students. I have a couple group shots of students over the last couple years here. And also I need to acknowledge that research costs money, and my research is funded by the National Science Foundation and the Department of Energy. And the other thing I want to acknowledge is that a lot of the pictures that I use for just basic graphics in this talk come from this textbook down here, Portrait of Planet by Stephen Marshak. Okay, so if you are interested in learning about what's inside the Earth and you Google, you're going to come up with a lot of pictures that look like this sort of classic textbook image of the planet where we see the various layers inside of the Earth and it's convection in the mantle and things like that. But if you keep digging, you will find other images and other ideas, and that is the hollow Earth, which is still quite popular on the internet among conspiracy theorists. And these folks have an idea that the Earth is basically a hollow shell, that there is a sun in the middle, and that it's very nice in there. There are entry and exit ports. I'm going to bring up my laser pointer. I forgot to do that. Okay, there are entry and exit ports at the South and North Pole. And inside, of course, there are intelligent and often compassionate aliens who fly around in flying saucers, and they come in and out of the North Pole. So before we laugh too much about what a silly idea that is, I just wanted to point out that the notion of a hollow Earth in some ways is very intuitive for humans, and that is because our perception of the world is basically it has evolved to fit our environment. We live on the surface of the Earth, and we experience the world as a bunch of surfaces that we cannot penetrate. So here is a beautiful picture of Four Corners in Arizona. And if we're standing here, we can look at that cliff, we can look at the ground, but we can't go down into the cliff. And so basically we work in this sort of two-dimensional surface environment. Another reason why the notion of a hollow Earth kind of persists is because up until a little over 100 years ago, we had extremely little knowledge of what was going on inside the Earth. So going back to that notion of our human need to have hollow surfaces, hollow places with surfaces in order to think about something, here is a scientific illustration, a really beautiful one by my friend Keelan Murphy, who is an artist. And it's very common in these illustrations, if we want to think about what's inside the Earth, even as scientists, we make a space in the Earth for our minds. So here's a cutaway. And then we project the information about what is inside the Earth on top of the surfaces of that hollow space. So that's kind of my thinking of the true origin of the hollow Earth idea. Okay, so there are two questions I want to talk about today. First, we'll talk about how do we know the Earth isn't hollow? And a related question is, how do we know what the Earth is actually made of on the inside? So I'm going to talk about direct observations, things we can see with our eyes. And then I'm going to talk about materials brought up by volcanoes. I will talk about meteorites and a little bit about the magnetic field very briefly. And then I will talk about seismology and mineral physics, which are the bulk of the meat of my talk, because that is the field that I am engaged in scientifically. So that is going from the beginning, the most intuitive ideas, things we can see with our eyes, to the least intuitive and the most sort of scientifically complex. So starting out with the intuitive, our direct information about the Earth's interior, stuff we can see with our eyes, we can think of as mines, which go up to about 3.8 kilometers deep into the Earth, and boreholes, which go up to a maximum depth of 12.3 kilometers. And rocks at these depths look just like the rocks on the surface. We don't see anything different as we go in. But I should point out that the radius of the Earth is 6,371 kilometers. So if the Earth was an apple and we were some kind of little bacteria-sized thing on the outside of the apple and we're digging into the apple, our boreholes, which is the deepest that we have direct knowledge, would barely pierce the skin of the apple. The next source of information we have going deeper is from volcanoes. Now, we all know that volcanoes erupt material from inside the Earth, and we see magma from inside the Earth spilling out on the surface in the form of lava. And that magma and lava can sweep along with it crystals and rocks that it basically grabbed while it was in the interior and brought out to the surface. So here we have a photograph of a basalt lava flow in San Carlos Olivine, and these green blocks are actually pieces of the upper mantle which were swept along with the volcanoes. Another, oh, here, I forgot. I have another sort of close-up of one of these rocks that volcanoes bring up, and most of them are a type of variety of rock called peridotite. And I will try not to burden you with too many excess words, but there are a couple mineral names that I really want you to remember. So in this peridotite, we see the majority of what it is a mineral called olivine. The gem name of olivine is peridot. It's this kind of pale green stuff here. It's mixed with pyroxene, and there are two kinds of pyroxenes in peridotite, a bright green one and a dark green one. So those are pyroxenes. And then sometimes we see other minerals like these pretty red garnets. Volcanoes bring us rocks from a maximum depth of about 250 kilometers. Now, that's for the rocks, but we actually have a deeper sample, and that is in diamonds. So diamonds are brought up in these rocks called kimberlites, in kimberlite pipes. And here's a diamond, a raw diamond in a kimberlite matrix. And you remember, diamond is very tough stuff. It's very, very strong. And where it may form at depths greater than the ones that the kimberlite find it at. So for example, here's a little diagram of the Earth, and the 250 kilometers is where the rocks from kimberlites come from. But the diamonds form at greater depths, and they can be swept along by the convective currents in the Earth mantle and form down here where the green star is, and they can go up deeper. So diamonds form, so far as we have found, at depths up to 1,000 kilometers. And the reason we know this is we can study these imperfections inside them called inclusions, where little bits of what was around the diamond when it started to grow get incorporated into the diamond. So here I have a picture of some minerals inside of a diamond, and you can actually see this is a gem cut diamond. So these are those sideways spaces on the bottom of the diamond here. And people in this study have used Raman spectroscopy to identify the minerals that they're finding in these diamonds. And I just wanted to give a shout out to some of my colleagues here at UNLV, Oliver Schauner and Shixun Huang, who a few years ago actually found inclusions of ice 7, which is a very, very high pressure form of water trapped inside of a diamond, which I'm just showing a picture from their work here, with a little area that has these little bright spots which turn out to be this ice 7. And all of the results from these deep diamonds, which have swept up materials from perhaps as much as 1,000 kilometers and carried them up to the surface, points to the chemistry at these great depths being really similar to what we see at those shallower depths. Basically, we have peridotite, we have little bits of aqueous fluids and some other elements that we see at shallower depths. So now I'm going to talk about the evidence from geophysics. We'll talk briefly about the composition of meteorites. We'll talk about magnetic fields, again, extremely briefly. We'll talk about seismology, and then we'll talk about high pressure laboratory studies, where we measure the physical and chemical properties of Earth materials at high pressure and temperature. And that is the business that my lab group and I are in. And basically, each line of investigation here is incomplete by itself, but together we can put together a very powerful picture of what's inside of our planet. So we'll talk about meteorites. So the Earth is part of the solar system, and the idea is that the solar system was formed from clouds of dust and gas. And meteorites are part of the solar system, and their story is linked to the Earth's formation story. And up here in the corner, I have a particularly interesting kind of meteorite called a carbonaceous chondrite. Now, carbonaceous chondrites are thought to be the primordial stuff that the Earth was formed from, sort of the unprocessed dust. And when we look at carbonaceous chondrites, they have olivine, pyroxene, they have some iron metal, and a little bit of organic material. So in a lot of ways, very similar to what we see in the upper parts of the mantle. Now, the other thing I want to mention is the presence of Earth's magnetic field. So I have down here a little illustration of the Earth's magnetic field sort of shielding us from the solar wind. And we're all familiar with the fact that we have a magnetic field. Well, the presence of that magnetic field basically dictates that somewhere inside the Earth, we have a lot of metallic iron. And we also see iron nickel meteorites, like I'm illustrating here in the bottom corner. And these are thought to be have formed in the core of a protoplanet that was subsequently completely busted apart by a collision. And so we have these little samples of protoplanetary cores that sometimes fall to Earth in the form of meteorites. So this is another kind of indication that our planet probably also has some kind of metallic iron core that goes along with its magnetic field. So now I'm going to talk about seismic evidence. So for those of you who don't think about seismology every day, I just wanted to sort of go back and remind everybody what seismology is about. So earthquakes, which are caused by shifting and faults deep in the earth, create sound waves. And those sound waves travel through the earth. So here's the idea of a fault. And this is the surface of the earth. At the top appears the sun and some trees. And inside the earth, we see those seismic waves radiating out from the source of the earthquake. Now, at the surface of the Earth, seismologists can place seismographs, and we can record and study those waves as they arrive at remote locations. So here's just another little diagram illustrating that idea. We have an earthquake over here. This is a cutaway section of the Earth. These little square boxes are seismographs, and the little lines are showing the various kinds of seismic waves traveling out to those seismographs and being measured. So if we know when the earthquake is, we know how far away the seismograph was from the earthquake, we can get a velocity for those sound waves. And down in the bottom corner, I just have a map of the International Federation of Digital Seismograph Networks that just show us that people all over the world have seismographs, and we share all of our data for earthquakes online, allowing scientists everywhere to study earthquake waves. I also wanted to remind you that we have two types of earthquake waves, P waves, which go fast, and S waves, which go slower. And P waves are very much like the kind of waves we have in the atmosphere that we call sound. They are made of sort of packages of compressed and extended bits of material, so that's what's being illustrated here. And these compressed bits and extended bits kind of travel through the air as our sound wave. And the S wave, less familiar because we don't have an analogy for sound in the air, is a sort of wave motion in the material, or often known as a shear wave. And so that's what's being illustrated over here. And the important part is these two a picture that is showing the global result for P and S wave speeds as a function of depth. I'm going to basically keep referring to this graph throughout the rest of my talk, so I want to take a moment and really break it down for you. So what we see at the top, going across the top, is the velocity in kilometers per second from 0 to 14 and higher. Okay, so that's the sound wave velocity. On the vertical axis is the depth going from the surface up here to the center of the Earth at 6,371 kilometers. On this plot now, we are showing the P wave velocity, that fastest wave, and how it changes as a function of depth. So you can see it kind of goes up and it wiggles around, and it goes up some more, and then it plunges and it comes back up, etc. And then we have the S wave velocities, which is doing something similar, but it's slower than the P waves. The other thing that's marked on here are those various layers of the Earth that we have defined. We have basically the upper mantle with the crust at the top. There's something called the transition zone. There's this sort of low velocity zone right underneath the crust. Then we have the lower mantle, the outer core, and the inner core. And interestingly, these layers are primarily defined by these P and S wave signals, because the behavior in the various regions allows us to put these lines here and say, okay, there's a big change here when the P wave plunges, or when we see the P wave bounce back up again. So I will be, as we go through the talk, I'm going to be referring back to this graph. All right. I did want to mention that, okay, I should go back. This graph is an average, a global average. So it's basically as if the Earth was the same going from the top down to the center throughout, right? So this is kind of averaging everything together. But the Earth is much more complicated. And we do have a technique called seismic tomography that I'm not really going to talk about, but I wanted to acknowledge it. And it's very similar to medical ultrasound or CAT scan in that we can use the multiple earthquake sources and the multiple receivers to build up a very detailed picture of the interior. And over here, I have a recent study from French and Romanowitz showing changes in the S-wave velocity in various colors in 3 dimensions. And so this actually is a piece of the Pacific Ocean. You can see the little green things are volcanoes in the Pacific. So the tops of this box is the surface of the Earth, and then the 2 sides we're going down towards that core mantle boundary at the bottom of the box. And so we can see we have regions where the velocities are slightly slower and regions where the velocities are slightly faster, these little blue blobs here. So seismic tomography gives us tremendous amounts of information about variations inside the Earth, but what it doesn't tell us is what the Earth is actually made of. It just tells us the speed. So we don't know why there are changes in wave speed from seismology, and we don't know what the sound waves are going through, which is where mineral physics comes in. So now I'm going to go to the part of the talk where I talk about high pressure laboratory studies, and in which we measure the physical and chemical properties of Earth materials at high pressure and temperature. Okay, so basically the game is to match the wave speed of materials in the laboratory to the wave speeds we see in the Earth. So wave speed depends on the state of the material. Gas, liquids, and solids are different states. That's what I mean by state. And so they change the wave speed. Wave speed also depends on the composition. That is, what type of minerals the rocks are made of. Wave speed also depends on pressure and temperature. So here is a good point to step back to the hollow Earth, and let's just do a test of the hollow Earth. So if the Earth is hollow, that means on the inside, at some place, we should see air. We should see the velocity of sound in air is 0.347 kilometers per second. And I've placed that at 25 degrees C, although temperature doesn't make a really big difference, because after all, there are aliens living in there and they should be pretty comfortable. And 25 degrees C is basically room temperature. Okay, so now here's that graph I talked about before with the velocity as a function of depth. And I have put this nice green line at 0.347 kilometers per second. And now we can compare the position of that line. And this is a P wave velocity, because remember, we only have P waves in air. So we're going to be looking at this line over here. And we can see as we go down in depth, there is no place in the Earth where the velocity of P waves is anywhere close to the velocity of sound and air. So that pretty much rules out the hollow Earth. Okay, so The next thing we can talk about is that function of the wave speed being a function of state. And I want to point out that S waves don't travel through fluids, which we've actually been talking about already, because that's why we don't have S waves in air. Now, the application of this that's interesting is if we have an earthquake, let's say here in this diagram where it says epicenter, and we look at the seismic wave signals on the far side of the planet out here, we actually don't see an S wave from those earthquakes. So here's a cutaway diagram of the Earth showing the focus of the earthquake, the ray paths of the sound traveling out from that earthquake, and then this thing we call an S wave shadow zone. So basically, S waves are able to travel along these paths here, but when they hit that region of the outer core, they can go no further, which produces the S wave shadow zone. So the S wave shadow zone basically tells us that the Earth's outer core is made of a liquid. It's still a very dense liquid. It has a P wave speed. It's not air, but it's not a solid. So that's an important fact to keep in mind as we go further. So Earth's outer core, from seismology, we know it is made of a fluid. Okay, so next, wave speed is a function of composition. That is the mineral. So, how are we going to know what to test, right? We have the whole periodic table we could wander through. But that would probably be a waste of time because we already have a constraint of the kinds of rocks that we find around on the surface. So for shallow depths, we will take rocks that we find on the surface, just a collection of sedimentary, igneous, and metamorphic rocks, take them into the lab, and we can measure the sound speed directly. And for those, we can also look at the rocks that come up in volcanoes, those peridotite, and we can measure the sound speeds of these. There's really no point in looking at, let's say, the sound speed of solid gadolinium or something, or because our Earth is not made of that. So when we do that, we find that for the very shallow parts of the Earth, the sound speeds of rocks that we have in the lab pretty much match the velocity profile that we see in this shallow part. Now at this point, you might be saying, wait a minute, we're up here on the surface, and when we look at surface rocks at room pressure, then we can measure velocity, fine. But how do we apply that to deeper inside? Because I did say that sound speed is going to be dependent on pressure as well as temperature. So that's what we're going to talk about next. How we get at this issue of measuring the wave speed as a function of pressure and as a function of temperature. So that brings the question about how do we make high pressure in the laboratories in a situation where we can measure sound speed? So pressure breaks down to force divided by area. And a familiar example of that would be a knife, right? So if we have a knife and we want to cut an apple, we can push harder, which is the force. When we exert the more pressure on the part of the knife that's cutting into the apple, we can push harder. Or we can get a sharper knife. We can push over a smaller area. So over here I have a scanning electron microscope picture of the edge, highly magnified edge of a knife. And the knife has a really tiny area on its sharp edge. And so that's basically how we get high pressure. Pushing harder is hard, but we can make finer points on things. So that is, in essence, the scheme that we use to produce high pressure in the laboratory. So I'm going to talk about two devices now that we use in high pressure studies. The first is the multi-anvil apparatus, and this is primarily the work in my lab group uses this device, and then we'll talk about the diamond anvil cell briefly. Multi-anvil apparatus is very big, and it goes to high but not super high pressures. The diamond anvil cell consists of 2 gem quality diamonds. That's what you're seeing here, gem quality diamonds, just like you would put in a nice solitaire ring with their little tiny points pointing at each other. And then you squeeze a little, basically, bit of dust in between the 2 of them, and you can study them. And so really high pressure, but really tiny sample. Multi-anvil, slightly bigger sample, moderate pressure. So I'm going to tell you now more about the multi-anvil apparatus. So it starts out with anvils, are basically big, strong metal bits that surround an empty space into which we put a block of ceramic that's bigger than the empty space created by the anvils pushing together. And inside of our block of ceramic, we have an open space in which we put our sample and a heater. And then we have, on the outside, we have a really big hydraulic press that forces the hard anvils together. So to illustrate that, I have some pictures. So we'll start with the sample first. So here I have, you'll see at the top, there's a ruler, and the little divisions are millimeters, right? So this is, an inch is going to be from is like 2.25 millimeters basically. So you can see this is, kind of really magnified. Here's my sample. It's this tiny little 1 by 2 millimeter cylinder, and we wrap it up in a little metal foil, and we make a tiny can out of it. Up here is you can see one of these cans that we make with our sample inside. And we put it inside a sleeve that sort of takes up the space around that, and then we put that inside of another sleeve that has a furnace. So here we have two sleeves that are put together. Actually, we have an inner graphite sleeve and an outer support sleeve. And the reason to point this out is this graphite sleeve conducts electricity. Nothing else here really conducts electricity, at least is contiguous from the top to the bottom of the sample assembly. So what we can do is we can pass a current through our sample and get this thing really hot and heat up our sample, which will be sitting in the center of this. So we put the whole thing together and to make these little cubes, and here's some other pictures of the little cubes put together, and you can see they're kind of not super pretty, but that's because they're put together with human hands under a microscope, and they're all these little fragile bits. So anyway, what we do is with those sample assemblies is we put them into the D-dia multi-anvil apparatus that we use. So here I have a bunch of pictures of the D-dia. Over here is that big picture the picture I showed you before of the apparatus itself, the whole hydraulic press. And this is actually sitting at a synchrotron beamline, which I will talk about in a minute. Inside the press, there's this module that I'm showing up here in the right-hand corner. And this is a cutaway, again, showing the top and bottom anvils and two of the side anvils pushing together with a little cavity in the center. And then over here on the left side of the picture, I have the real deal. So you can see down in the center, there is the top of my little tiny sample assembly. These are tungsten carbide anvils, and you can see three of them. There's another one pushing from in front of the picture. There's one underneath. It's buried. You can't see. And then there would be another one pushing down from the top. And those 6 anvils pushing together squish the sample and create very high pressure when the hydraulic press sort of pushes all these things together. All right, so next, this is an after picture. So you can see what happens to the sample assembly. Here are 3 of the side anvils, the bottom anvil, and you can see my little cube that we put in there gets just completely mashed and these little fins extrude out. But when this is all assembled at high pressure and under load from the hydraulic rams, we have quite high pressure in the interior, and that's where our sample is. And again, we can flow current through these anvils to get the sample hot. And the little wires are, in this case, measuring the temperature. That's a thermocouple. Okay, so we have a bunch of options for what we can do in this kind of apparatus. We can study the sample while it's at high temperature and pressure, and we refer to that as in situ. We can make ultrasonic measurements, so those are basically sound measurements. We can shine synchrotron X-rays through our sample and see what's going on inside. And we can also take the sample out after our experiment, and we call that cook and look. And we can look at what happened to it in the microscope. So just for those of you who are not familiar with a synchrotron X-ray, synchrotrons are big national facilities. On the left side of the diagram, I have a sort of a diagram of the National Synchrotron Light Source, which has been now updated to be the National Synchrotron Light Source number 2, but this is a floor plan of the original synchrotron, LS1. And what you're seeing is the inside of a very large building. So if a person, in this diagram, you can see actually on one of these little green boxes, there's some little tiny squares. That's kind of like the size of a person. So basically these green boxes are what we call hutches. They are little buildings that we can go inside. And the anvil is here, the multi-anvil here is sitting inside of one of these hutches. So going back to the synchrotron, the way it works is that we have a ring in the center, and inside this ring we are sending electrons around in a circle at very close to the speed of light. And when we accelerate electrons in a vacuum at close to the speed of light, they spray off intense X-rays, X-rays that are strong enough so that when we want to find where the X-ray beam is, we just have to put a piece of paper up and see where it sets it on fire. Now, these X-rays will sterilize anything in their path and they will burn people. So we surround the ring with a big lead wall, which is out here. And then to get the X-rays out where we want to use them, we just poke a little hole in the wall. So you can see here, there's a little wall with a little purple line coming out of it. That's showing where the X-rays come through little holes in the wall. So once it comes out of the wall, we surround those X-rays with a beam pipe, shields everything, keeps people from walking into the beam. And then we steer them, we allow them to pass into these little lead-lined buildings, which we call hutches, which is where we do our experiments. So we can put our apparatus in the hutch, and then we can do our experiment and go in and out, and we can, it's basically like a shutter. We turn off the X-rays when we want to go in, and then we come out and we turn the X-rays back on. So this is just a sort of a little diagram showing how we measure sound speed. So this is a sample assembly kind of cut in half. So you can see the sample and the bottom anvil, and we can send sound in and have it bounce off the edges of the sample and come back out. And we measure those sound waves, and we can actually compare the speed, the travel time of the sound waves going in and out to the length of the sample, which I'm showing over here in this kind of gray box. This is kind of a shadow. It's more like a regular X-ray image where we can see the top and the bottom edges of the sample and allows us to know exactly how long the sample is. And we can also make diffraction measurements of the sample, and I will talk extremely briefly about that in just a second. Okay, so from making sound wave measurements in an apparatus like that, we can actually see that we can match P and S wave velocities for things like olivine and pyroxene all the way down to about 400 kilometers depth. So making that match allows us to be quite confident that what is in the upper mantle is indeed a mixture of olivine and pyroxene. Now I want to talk about the next region, the transition zone. So before I go there, I just want to remind you that we can have multiple phases with the same chemical composition. And the classic example is diamond and graphite, right? They're both carbon, but they have very different physical properties. So olivine and pyroxene are similar. They are low pressure minerals that can transform to a new pressure at higher they can transform to a new structure, just like the difference between graphite and diamond, at higher pressure. And here is an optical micrograph from some of my research just showing a transformation like that, where we have the original olivine crystals in the bright colors. These are false colors from the microscope. And then the new crystals of the denser phase are forming in the edges of the original crystals, and they are the dark color. And here's an example of the kind of data we can collect at the synchrotron. These are X-ray diffraction patterns. It's not super important to explain exactly what you're seeing, but I just want to point out that the little O's, you see the little boxes from the O's, those are peaks, which are indication in diffraction of the presence of olivine. And then there's these other little boxes that have a gamma, it looks a little bit like a Y. Those are indication of the presence of the spinel phase. And then there's another high pressure phase called beta, which is indicated in these little boxes here. And on the side of this diagram, so I have time and changing temperature. So what I've done is I've taken a whole series of measurements that we made over probably a 24-hour period where we changed the temperature as as time went by, because that's we live in time, if we want to do anything, we have one temperature and then there's another time and we can change it to another temperature and make a measurement. So as we go through our experiment, changing temperature, we can change the nature of the phase that we see in the experiment. And doing experiments like this allows us to build, I think I skipped a slide there. Yeah, it allows us to build things like this, which is a phase diagram. So on this axis is temperature, and on this axis is pressure. And it's showing us the temperature pressure regions where olivine is stable and where that beta phase is stable, the gamma phase, and then ultimately this phase called perovskite. And then you can also see where olivine melts. And we can also do that kind of work, not so much me, but my colleagues, on the mineral is called pyroxene. And we get a similar phase diagram where we have lots of different phases. And then as we go to the highest pressures, we get this thing called perovskite. So the measurements from the lab, and meanwhile, we can also make these things like clinoacetate or ilmenite, and we can measure their sound speeds, just the way I was talking about before. So that science basically gives us a basis for understanding what's going on, this sort of choppy change in the sound speed in the transition zone. And then it also explains why after the transition zone, where we have this very complicated assemblage of minerals, we suddenly find ourselves in a region where things just increase at a fairly constant rate, the same way they do in the upper mantle. And that is because we have reached this pressure where perovskite is stable for both pyroxene, and for olivine, it's perovskite plus MgO. So that's what the lower mantle is thought to be made of. And that gets us basically to the pressure limit of the multi-anvil. So the multi-anvil can get us very confidently sound speeds and phases up to the upper part of the lower mantle, but we can't get any deeper. So for here on, I'm going to talk just briefly about the diamond anvil cell, which is how we investigate the remainder of the Earth. So the diamond anvil cell, as I said before, consists of two gem quality diamonds that are pointing towards each other. We have a little gasket in between that holds our sample, keeps it from squirting out the side. So we have basically a fleck of dust in between those two pointy diamonds. And what's really cool about this instrument is that we can look at our sample while it is at high pressure with our eyeballs. Using a microscope, we can measure them with x-rays, and we can use all kinds of other spectroscopic techniques. So here is a picture looking down the axis of the diamonds this way, and we see a little fleck of that MgO material I mentioned that goes along with the perovskite in the lower mantle. This was actually done by Jennifer Jackson, a colleague of mine at Caltech. So what she can do is she can put materials in her diamond anvil cell, crank them up to lower mantle temperatures, and then actually look at them while they are at the pressure and temperature conditions of the lower mantle. And we can make all kinds of measurements that way. Okay, so this device can achieve pressures exceeding that of the center of the Earth. And therefore, we have the entire rest of the planet covered with the diamond anvil cell. So here's just a picture of how this thing works. So here's the guts again, those beautiful gem quality diamonds pointing at each other with a little gasket holding our fleck of dust in place. And the cell itself is just a steel item that holds the diamonds in place. So this is what it looks like on the outside. And I should say that's 5 centimeters, so it's relatively, kind of fit in the palm of your hand, basically. And the diamonds, if we could peer inside here, there's a little port in the side, we would see these diamonds. So they're held in place by the steel body of the diamond anvil cell. And then it has these little screws that allow us to tighten the diamonds together and control the pressure that we can create inside. Now, to heat the diamond anvil cell, we have a couple of options. One is to wrap the interior portions of the cell with little heater, basically toaster wires, same stuff as toaster wires. So here in this diagram, I have my 2 diamonds, that's sort of a extra fat looking gasket, just so you can see the sample in the center. And then the thing that's holding the diamonds in place, these tungsten carbide seats, we call them, can be wrapped with the little dots, or to illustrate a coil of wire that's wrapping around the whole thing. So that will give us sort of modest temperatures up to 1200 degrees C, something like that. If we want to go higher, then we use lasers. So here is a little illustration of a DAC in the center, and the orange lines are lasers that are being shown into the diamond anvil cell. And we can heat our sample with lasers to just tremendous temperatures, very easily temperatures of the center of the Earth, the photosphere of the sun example, we can get just incredibly hot. Okay, so just to show how this is applied, I will take one example, and that is the core. So the core is thought to be composed of iron, and that's because of the density of the planet, the composition of meteorites. Remember, those chondrites had iron in them, and we have seen iron nickel meteorites, and also the presence of a magnetic field. And from seismic waves, we know that the outer core is molten and the inner core is solid, which means that the outer core conditions are going to pass across the solid liquid phase boundary. So here's just that illustration reminding us that the outer core is solid, but we see S waves in the inner core, which means that this thing, and so the outer core is liquid, I'm sorry, and the inner core is solid. So this is where we see S waves in the inner core. All right, so people for years have been working on studies of iron melting using the diamond anvil cell. And the reason they've been working on it for years is because it's extremely challenging to get a good measurement of the temperature. When you get to extremely high temperature, sometimes it's hard to even measure what the temperature is. And of course, you're pushing these little diamonds together with a great deal of force. A lot of times they just kind of blow up into little tiny fragments, which is very sad because they are expensive. But despite the challenges, over time, these experiments have allowed us to constrain the temperature and pressure, the temperature profile of the Earth. So I'm going to show you that. So here's some results from some recent experiments on the phase diagram of iron. On the y-axis, again, I have temperature, and you can see these are really high temperatures, 6,000 degrees Kelvin. And on the bottom axis, I have pressure. And at the top, they've illustrated how that pressure goes along with the structure of the Earth. So here you can see the inner core, outer core boundary, which I have highlighted in green. And the little symbols are various experiments that these authors did. And so they could locate where the liquid field is. So here you can see it says LIQ. So up here, above this black line, the iron is molten. And then below, where it says HCP and FCC and BCC, these are various structures of solid iron. And they're just showing their sample here in the diamond anvil cell that they can actually look at it and see what's going on. So the fact that at the pressures of the inner core, where we know the iron is solid, tells us in the measuring this liquid solid boundary tells us that we have to be at the inner core, we have to be below the temperatures of the smelting line here, right? So the last thing I want to point out in this diagram is that we have this gray area. These are kind of possible geotherms. That is, geotherm is the temperature of the Earth at depth. And these are the sort of range of geotherms that various people have put out there in the literature. And what this is telling us is that basically at that inner core, outer core boundary, the Earth's temperature has to be here at roughly 5,000 K. And so this gives us a pinning point for that temperature as a function of the depth in the Earth. So,
Dr. Burnley?
Yep.
I'm just giving you a 5-minute warning. It's
Okay,
12:53. So whenever
super.
you're ready.
I am just about, because this is my second to last slide.
Excellent.
So just to sum up, by combining the physical properties that we can measure in the lab with seismic data, the seismic data being off on the left, we can figure out a nice, really robust picture of what is going on inside of the deep earth. And again, this is kind of a more of a cartoony illustration of the idea that we have, these convection currents, and we have things sinking into the inside and coming back up in the form of volcanoes. So we have this really complicated picture of a place we have never been before and have no hope of going to. But because we have seismology and we can combine that with the kind of lab experiments we do here, we can be fairly confident that we know what's going on. And I can assure you all, there is no need to worry about aliens. So thank you very much.
Thanks so much, Dr. Burnley. That was great. Really appreciate it. I actually, if anyone has any questions, please put them in the chat and I'll ask them to Dr. Burnley. But I had a question for you, and it relates to kind of what you talked about at the beginning, how we've only gone we barely pierced the skin if we were an apple, for example. Is that because we can't get below that level? Why is it that we haven't been able to go any deeper? You there? Did you hear my question, Dr. Burnley? I can't hear you.
So is that the question?
There you go, you're back. Oh, we might have lost you again. Can you hear me? Well, I think we're having some technical issues with Dr. Burnley's sound. I can't hear you. Probably just a microphone issue, but it looks like she left the meeting. She might be coming back in when she disconnected her presentation. But thanks everyone for joining us today. And again, please put any questions in the chat. It looks like Dr. Burnley is going to log back in.
Hi, I am so sorry. I hope,
That's okay.
You got the whole talk, right?
We did, yeah. The talk was great. It's just when I asked the question, we couldn't hear the response. That was the only thing.
Yeah, I think I lost you midway through the question, as a matter of fact. So can you ask the question again?
Sure. So you're talking about the apple.
Hey, can you hear me, Corey?
Yeah, I can hear you, Eric.
This is Eric, and I'm no good at typing, so I'm just going to talk. How's that?
Go for it.
So Pamela, maybe I remembered this wrong, but years ago, I remember a report where they used seismic data to not only say the core was solid, but that it was crystalline and almost single crystalline, in the sense that seismic waves had different speeds going different directions through the core. That it got even more amazing than that, in the sense that when they did it over time, they said the core was rotating at a different rate than the planet as a whole. Did I imagine that? Is that all fiction?
No.
Has it been proved correct or wrong?
I actually don't know where we are with core superrotation at the moment. There's that's the name of the idea, core superrotation. And that idea was out there for a while, and I haven't heard anything lately. And there's so much to know. I haven't kept up on everything. Now, the idea that the core could be essentially a single crystal I think that's still out there. It could also be, rather than one big single crystal, it could just be a lot of little tiny crystals highly aligned, in the same way that, let's say, a wire. If you looked at the crystals inside a wire, they would also be highly aligned because of the way the wire is fabricated. So yeah, there's a very strong possibility that the inner core may have what we call fabric, a very strong alignment of the crystals inside.
Thanks, Dr. Burnley. I had a question on how, so why we haven't been able to go any deeper into the core and explore it more. So
Yes.
is that like lack of equipment? Has it just not been done? Or why is that, why are we not able to know, or why haven't we gone deeper, I guess?
Okay, so what happens, the deeper we go, the harder it gets to go there. So for example, for mines, that deepest mine that I mentioned, which is in South Africa, I believe the temperature of the rock in the walls of those mines is 150 degrees C, which boiling point for water is 100. So that's really uncomfortable. And sort of like you wouldn't really want to go any deeper if you're a person, maybe if I'm a robot. But metals all have melting temperatures, and as they get warmer, they get more easy to deform, even if they're still solid. So it's harder and harder to get your equipment to work properly as you dig deeper and deeper. So these very deep holes, like the one I mentioned in the Kola Peninsula in Russia, they're extremely hard technologically to get any deeper. And they're also intensely expensive. So there has to be some really good reason that you want to go down there. And because we have all these other techniques, there's not a lot of, super exciting science for digging these really deep boreholes. So it has, there has to be some commercial driver, something like in a gold mine where people really want to pull stuff out.
Got it. Thank you. That's very interesting. And thank you again for this talk. It was so fascinating and really, I think something that most of us don't think about daily, but it's something that is around us all the time. So thank you again. It was wonderful. I don't believe there's any other questions in the chat, but I know Dr. Burnley is always available if you have questions or want to shoot her an email. Feel free to reach out to her, and she can answer any questions that you might have. And thank you all again for joining us today. It's been great.
Oh, well, thank you for being here and listening to my story. I appreciate having the audience.
Well, we appreciate you joining us today. Thanks so much, Dr. Burnley. Okay. And thank you, everyone. Have a great afternoon.
Okay, thanks. Bye.
Bye.